What we have depicted here in these four images are matter in different states. And we're using what's known as a particulate model. And these are two-dimensional particulate models, which are simple ways of imagining what is going on at a molecular scale inside of matter. And so you can imagine each of these circles to, depending on what we're dealing with, it's either an ion, it's a molecule, or it's an atom. But it's telling us how these molecules or ions or atoms are interacting with each other, which determine what state of matter we are in. So pause this video and think about which of these quadrants represent matter in a solid state, which represent matter in a liquid state, and which represents matter in a gas state. All right, so there's a few that might have been somewhat obvious to you. If you imagine each of these circles to be an ion, you could imagine these to be ionic solids that we've seen, that type of lattice structure. If you imagine each of these circles to be atoms that are forming covalent bonds with neighboring circles, then you could imagine this being a covalent network solid. If you imagine each of these circles are molecules, and due to intermolecular forces, they have arranged in this regular way to the other molecules, then you could imagine this is a molecular solid. You could also imagine that each of these are metal atoms, and they're all sharing the soup of valence electrons, and so we are dealing with a metallic solid. But no matter which visualization you use or what you're imagining this to be, it's pretty clear that this is a solid. And one of the major giveaways of that is that it's not taking the shape of the container. These molecules, I guess you could say these particles, aren't able to fully slide past each other and take the shape of the container that they're in, which would happen in a liquid. And they're clearly not able to overcome the forces between the particles to then go off and do their own thing, which we would see in a gas and bounce around the entire container. So this is clearly a solid. Now this one on the bottom left, here it does look like the particles are taking the shape of the container. They are able to slide past each other, but there are still intermolecular forces there that keep them from flying apart. So this is clearly a liquid. And in this bottom right quadrant, you could imagine what's going on. These particles, whether they're molecules or ions, they have, for the most part, been able to overcome the intermolecular forces between them. And so they are just bouncing around, fully taking the form of the container that they are in. And so this is a gas. Now what about this right over here? It looks kind of like a solid in that it's not taking the shape of its container, but it's also irregular, the way that you might expect a liquid to be, at least at a snapshot in time. And this, because it's not taking the shape of its container, and because these molecules or these particles, even though they are irregular, they aren't sliding past each other like you would expect in a liquid. This too is a solid, but we call this an amorphous solid. It does not have this nice crystalline structure like we've seen with the crystalline solids. And there's a lot of examples of amorphous solids. Most of the solids you know in your life that are stretchy, that have an elastic quality to them, are amorphous solids. For example, if you had a little bunch of natural rubber, you could pull on it, and it might look something like this when you stretch it, but then when you let go, it will go back to its original state, or maybe close to its original state. And the reason why it does that is natural rubber is made up of polymers. And just to imagine what a polymer is, this is a molecular structure of actual natural rubber. It's a chain of carbons that are bonded to hydrogens. And if you imagine it, if you were to zoom out from this, you imagine these chains, these very long chains of carbons with hydrogens. And then in natural rubber, they all get tangled up with each other. And so they're forming this amorphous solid. It doesn't look exactly like this particulate model we just saw. It's more, just imagine a bunch of strings that are all tangled up. And so if you were to pull on them, they are able to stretch, but then you let go, they get back to close to where they were before. Now, rubber isn't the only polymer. For example, the plastics you see all around you are also polymers, and a few are mostly amorphous, and then a few are mostly crystalline, and a lot are what we would call semi-crystalline, which means they have both amorphous and crystalline regions.